This video is going to review how to calculate the expectation value of a quantum mechanical observable. So first, the expectation value is simply the average value that you would get on a quantum mechanical after making a quantum mechanical measurement. So when we make a quantum mechanical measurement, we're not guaranteed any outcome, but we can know the probabilities of the outcome we can get, and we can use that information to calculate the average value, even if we can't know the exact values of any measurement we're going to make. So the way to calculate this value is to simply evaluate this integral that's on the screen. So if we want to know our operator, our observable A, we need to integrate from negative infinity to infinity, all the space we're interested in, of the complex conjugate of our wave function, and then we multiply that by our wave function that has been operated on by the corresponding operator of the observable that we're interested in. Now, there's a couple of situations that we can use, or we want to know the expectation value for. So first, what if our wave function is an eigenfunction? Well, then it's actually a pretty simple problem. So what we can do is recall what happens when we operate on an eigenfunction with its operator. So if our wave function here is going to be equal to, say, the second eigenfunction of the operator, and again, we're just changing the functions here, it's all arbitrary. But if we operate on this function that is an eigenfunction with its operator, what happens? Well, we always get our function back multiplied by a constant. So in this case, we'll get our v2 multiplied by a little a2, where a2 is just a constant. That's the definition of an eigenfunction. And this is going to help us solve the integral. So now if we come back in and we want to solve for the expectation value of a here, we're going to integrate over all space of the complex conjugate of our wave function, and then multiply that by our wave function that's operated on by our operator A. Now, with our operator A, again, we're operating on an eigenfunction. And so that means, what do we get? Well, we get a constant A2. And we always get that. Now, we can take this and simplify it, because A2 is a constant, which means we can pull it out of the integral. So we'll pull it out, and that gives us the integral from negative infinity to infinity of the complex conjugate of our wave function times our wave function. And now we're going to take advantage of one of the properties of wave functions, and that is that these wave functions are normalized. And if these wave functions are normalized, that means that this whole integral here is equal to 1. So that means the expectation value is just a2. And this makes sense because here our wave function is just one eigenfunction of the operator, which means when we operate on that wave function, we can only ever measure that one value. Now, what if our wave function isn't an eigenfunction? That makes our life a little bit more complicated, but not very complicated, actually. So there's a couple of situations that we can imagine here. And first, let's imagine one where our wave function can be described as the sum of different eigenfunctions of the operator. So for the sake of just doing the math, we're only going to assume 2, but this will work for any number if we can break our wave function down into any number of eigenfunctions of operator A. So let's assume that our wave function is equal to b1 phi1 plus b2 phi2, where phi1 and phi2 are eigenfunctions of our operator A, and then b1 and b2 are constants that determine how often that phi1 and phi2 would be measured, or how much our wave function looks like phi1 and phi2. So now we can evaluate the integral just like we've done before. Now, at first, it's going to look a little bit messy, but it will simplify out in the end. So the expectation value of A, again, is equal for the integral of negative infinity to infinity of our wave function, which in this case is b1 phi1. And now this is the complex conjugate, so I'm going to star all of these terms over here, plus b2 star phi2 star. And then it's our wave function again operated on with operator A. So operator A, then b1 phi1 of x plus b2 phi2 of x. Okay, so we have a lot going on here, but let's break it down. So first, we are operating on two eigenfunctions of operator A with operator A. That means that all that is multiplying each of those terms by a constant. So you can break that down and say that this is equal to the integral from negative infinity to infinity of b1 star phi1 star of x plus b2 star phi2 star of x. And then now this is times a1 b1 phi1 of x, because we operated on our wave function, our eigenfunction phi1 with a, which gives us a constant a1, and then plus a2 b2 phi2 of x. Okay, so here we'll need to multiply this out. That will give us 4 integrals. But like before, we'll see that these integrals are actually easy to evaluate even for arbitrary functions. So I'm going to split it apart into 4 integrals. The first integral will be this one. So we'll take all the constants out of the integral as well as we develop it. So first we'll have a1, and I'll write this here. So the magnitude of b1 squared, which is just b1 star times b1, and those are the constants, and that's integral equal to multiplied by the integral from negative infinity to infinity of phi1 star of x phi1 of x dx. All right, and you'll recognize this form over here, but let's keep going. So then the next function we'll get is going to be a1 b1 b2 star times the integral from negative infinity to infinity of phi2 star of x phi1 of x dx. And I'm going to copy all of this here because the next two integrals are going to be very similar. So the next two integrals that we get are going to be, instead of having our a1s here, it's going to be a2 and b2 star, and we'll change the indices here as well. So just multiplying out those other two terms. And then at the end here, we'll switch all of the b1s and b2s as well. So we'll have a2, b2, b1, and then phi1 star times phi2. Okay, so this kind of looks like a mess, but it's not. So what we're going to do is first realize that our eigenfunctions are normalized, just like in the last case. So these two integrals here are both equal to 1. So that simplifies that a great deal. And we still have two other integrals, and we're going to simplify this. We're going to recall that our eigenfunctions are orthogonal. So they're not only normalized, they're also orthogonal. They form an orthonormal set. And the fact that they're orthogonal means that when you integrate the complex conjugate of one eigenfunction times another from the same set, that's equal to 0. So both of these integrals over here are equal to 0. So that means our average value for a is simply a1 times the complex conjugate of b1 squared, the magnitude of b1, plus a2 times the complex conjugate of b2 squared. And that's it. So here we can see what we're going to end up with is a weighted average of our two expectation values. And this makes total sense as well. If we have a 75% chance to measure A1 and a 25% chance to measure A2, you would just need to multiply A1 by 3/4 and A2 by 1/4. And that's going to give you what you get on average. If you make 100 measurements, you're going to get 75 A1, 25 A2, and you're going to get the same average. So that is how you can easily measure the expectation value if your function can be broken up into eigenfunctions. In the third case, again, if we don't have an eigenfunction, and we also may not be able to simply break our function up into eigenfunctions of the operator. So one common example for this is going to be the position operator. So maybe we want to know the average position of a particle. Well, in that case, you're actually just going to have to go and solve the integral. And in this case, these integrals are typically going to be easy to solve. So for example, maybe we want to know the average position of our particle in a box. So we're going to integrate over the box length here, 0 to a, and we're going to integrate the complex conjugate of our wave function and then operate on our wave function with position operator x. And in this case, our wave function for the particle in a box is 2 or square root of 2 over a, which is going to get squared since we're squaring our wave function, times sine n pi x over a. So we're going to have that squared as well. So we'll have x sine squared of n pi x over a. So this is an integral that we don't necessarily want to be able to solve easily. We can look up how to do this integral. This isn't a math course. So we can do that. And when we do that, what we'll find is we get an answer of a over 2. So I encourage you to go look that up, solve that integral, and see if you get a over 2, which is exactly in the middle of the box. So again, this review covers how to calculate the expectation value. Remember, the expectation value is just the average value. And typically, the way we'll calculate the expectation value is going to be in these forms, because we won't often just have a simple eigenfunction. But if our eigenfunction can be easily broken apart into, or our wave function can be broken up into eigenfunctions of the operator, we can use this method here. And if it's not, we have to actually go and evaluate the integral using this method here. In any case, both of these methods, and the first one as well, all rely upon solving this integral. So this is the key integral that you'll want to remember to solve for the expectation value.